Vortices are two-dimensional solutions to soliton equations. When you think of a vortex, you might think of a swirling whirlpool as shown on screen. We'll find that actually they are slightly more boring, but they have interesting properties. In 2 dimensions, their cores are simply points, but in 3 dimensions, their cores can be curves, and they can form what is known as a spaghetti of vortices, which has its own complex dynamics. We shan't be covering those here. We focus on static fields in the global theory. We study these by looking at functions of their energy known as Ginzburg-Landau functions. These functions are naturally invariant under rotation, which means that if you have one solution, rotating it around the z-axis will give you a whole family of solutions. We can see by mapping phi of x to e to the I alpha phi of x and observing how the e to the I alphas cancel that the invariance is within the equations themselves. By varying the Lagrangian potential V with respect to phi and the complex conjugate of phi, we obtain field equations as written. What is U? U of x is a quadratic in x with parameters mu, and lambda. This means that it is also quartic in the absolute value of phi. We impose that lambda must be greater than 0 for it to be a positive quartic, and mu to be less than 0 so that our solutions remain interesting. We can then rewrite this quartic as u of the absolute value of phi squared equals lambda over 8 times m squared minus the absolute value of phi squared squared. Plugging back into our original energy equation, we get that V equals half times the integral of the gradient of the conjugate of phi dot producted with the gradient of phi plus lambda over 4 times m squared minus phi squared squared. We can vary with respect to the complex conjugate of phi to get the Laplacian of phi plus lambda over 2 times m squared minus phi squared times phi equals 0 as our field equation. From now on, we'll set lambda equal to 2 and m equal to 1 for simplicity. In Ginzburg-Landau model, the energies sadly cannot be finite. We compensate by looking for solutions with logarithmically divergent energies. We classify these solutions depending on a property of theirs called their winding number, which is the amount of times the solutions go round the z-axis before returning to themselves. If n equals 1, we call the solution a vortex. If n equals -1, we call the solution an anti-vortex. And if the magnitude of n is greater than 1, we call the solution a multivortex. Since our solutions are circularly symmetric, we use polar coordinates, and so we're looking for phi of r theta. We first consider a solution that is rotationally invariant, so that phi of r theta is equal to phi of r theta plus beta. We also wish for our solution to have reflectional symmetry, otherwise it would just be on the positive real line. Hence, it must be real and have 0 winding number. Turning back to our Ginzburg-Landau equation, we substitute it in to get this Laplacian potential, which yields our variational equation, which has the trivial solutions phi equals plus or minus 1. These aren't very interesting, so we turn to the numerical method of finite differences to search for other results. One can numerically solve differential equations essentially by making great use of the approximations of derivatives using the limits definition. For example, if we're dealing with the differential equation d2y by dx squared minus y plus 2 sine of x equals 0, we can discretize the x-axis and use approximations at each x point using these approximations for the derivatives. As we can see, this isn't the best method and it rapidly can diverge. For certain equations, such as the ones we are dealing with, a better way of doing it is to actually make it more complex and turn it into a partial differential equation. Instead of being equal to 0, we set our equation equal to the partial derivative of y with respect to t. We then guess the initial solution, and the equation will act like the heat equation and dissipate energy until the graph settles to the solution, as this is when the partial derivative of y with respect to t is equal to 0. We can see this here. We do this numerically the same way, but in this case we discretize both space and time. For the first equation that we are dealing with, we can similarly discretize and do the same procedure, yielding us this quite complex numerical formula. Here we see that unfortunately the solution tends to the trivial solution of phi equals 1, and thus we can end our search for the simple case of winding number 0. A more interesting way to preserve rotational symmetry is to increase the winding number. We can encode this mathematically by letting phi of r theta be equal to phi of r theta plus 2n pi, which means that phi of r theta equals e to the in theta phi of r 0. We return to our Ginzburg-Landau energy equation, which this time has the potential written below, which reduces to the field equation there, which we give boundary conditions phi of 0 equals 0 and phi of infinity equals 1. And again we have to return to our finite difference model to search for solutions. Again we set the equation equal to the partial derivative of phi with respect to t and discretize the model. From this we can generate a solution, such as this one, that the winding number n equals 3.